Hi everyone, welcome to another video of this channel. So today we will be talking about the epsilon delta definition of a limit. And this will give us a way to formalize our definition of a limit, because a limit is usually defined as something approaching something as something else approaches something else. But what does approach really mean mathematically? So that's what we will be looking at today. So suppose we have a function f, and at a point a, this function has a limit L. Now, of course, this function doesn't have to be defined at a, but as long as x approaches a, f approaches L, the limit will exist and be equal to L at point A. So that's kind of our more intuitive definition. Now let's try to formalize this. So I'm going to draw these dashed lines, and first of all, in order for this limit to exist, f has to be defined on some interval containing a. Not necessarily at A. Uh, there could be a hole in the graph, but f can't have a huge wide gap. Of course, there won't be any limit in that case. So that's kind of what our preliminary assumption is. So then, limit as x approaches a of f of x equals L. Uh, we can define this by saying that for any epsilon, where this upside down a is for any, there exists a delta. This backwards e is there exists, such that 0 is less than the absolute value of x minus a, which is less than delta, implies that 0 is less than f of x minus L, which is less than epsilon. So that was definitely a mouthful. And what does this even mean? So let's try to dissect this. What this definition is saying is that no matter what epsilon is, uh, any epsilon should make this definition yield to the definition of a limit, as long as there exists a delta for which this condition is satisfied, then there will be a limit, right? So this for any there exists pattern is actually a very common pattern in math, and this is just an example of this pattern at work, but this actually pops up in a lot of other mathematical definitions and theorems. So graphically, what does this mean? Well, so basically we have this interval from L minus epsilon to L plus epsilon. And we'll mark it by these dashed lines here. And we also have this A minus delta to A plus delta, marked by these dashed lines here. And so what this definition is saying is that if x is in this interval, and once again, not including A, right, then f is in this interval, not including L. So if this, then this. And again, for any epsilon, as long as there exists a delta, this limit will exist. Now, it seems logical, right, that no matter how small, right, how small we could make epsilon, no matter what, as long as there exists this delta, right, we can make delta arbitrarily small. So if we make epsilon arbitrarily small, we can make delta arbitrarily small. That's basically why the limit exists. Now, to demonstrate why this is true on our specific epsilon, notice that at this rightmost extreme point a plus delta, our function value represented by the dashed line will be between L minus epsilon and L plus epsilon. Similarly, at the leftmost extreme point of this a plus delta, a minus delta interval, the value of f at a minus delta will still be in this interval. So for this particular epsilon, this delta, for example, works, and we can make epsilon arbitrarily small, and we can always be able to pick a delta for which, if x is in this interval, f will be in this interval. Now, in general, this might still be a bit confusing. And in general, when we are talking about definitions, it is useful to see why they break down when what we are defining doesn't happen. So why does epsilon delta break down when there is no limit, right? So suppose we have this jump discontinuity, and we have this function f, but it has two branches, right? There's this jump over here. Now we know that no limit is defined here, but suppose we try to define a limit L at point A, and suppose that we go with this value and not with this value just because f is defined there, but our argument will work the same regardless of where defined L. So we again draw our ranges from L minus epsilon to L plus epsilon, and from A minus delta to A plus delta, and basically, if x is on this interval, then it should be true that f is on this interval. For any epsilon, no matter how small or large. there must exist a delta for which this is true. But if we try to find such a delta, we immediately into a problem. Because, as it turns out, epsilon can actually only be greater than the size of this gap. For epsilon smaller than this gap, we cannot find a delta for which, for all x in a minus delta to a plus delta, f will actually be inside the L minus epsilon to L plus epsilon range. Consider this point right here. At this point, f will be at this value, right? And this is outside of the L minus epsilon to L plus epsilon range. And this is no matter how small delta is, right? We can try to make delta as small as possible, as close to a. There will still be some value that is outside this range. But this definition must work for any epsilon, not just epsilon bigger than this range. And because of this, we know that by the epsilon delta of the definition of the limit, there is no limit at this point, right? Not only is it not equal to L, but if we try to find it anywhere else, this will also break down. So there is no limit for a jump discontinuity. But we might remember that a point discontinuity, where the function is continuous except for just at one point where it isn't defined or equal to another value, just like sine of x over x, for example, right? Those functions actually do have limits. And so how does this work, and how does this obey the definition? So suppose we cross out this branch of the function, we lower it a bit, and then suppose that we define it instead of at L, we define it at this point. So this function is not continuous, but we will show that it actually does have a limit. So this is a point discontinuity, but it still satisfies the definition because we specified that delta must be larger than 0, strictly bigger than 0. What does this mean, and why does this apply? Well, notice that no matter how small or large epsilon is, there will always be a delta, right, for which any value other than a will be in this range. We don't actually care what happens at the value a. And if we try to do the same thing that we did here, right, try to find a value that is above, that would only work at a because that is the only place where this function is actually outside of that interval. And since we specified that we don't care what happens at a in the definition, we know that this actually does follow the definition and this limit does exist. And this is actually the specific case why we had to include the bigger than 0 in the definition. So this continuous function can still have limits. They just won't be equal to the value of the function at that point f of a, but as in this case, they will be equal to some value lower or higher, like L. And so this is kind of the theoretical part. Now let's see how we can apply it, right? So this is how to show that epsilon delta leads to this limit statement. So the first step is to say that for all epsilon bigger than 0, right? We want for all positive epsilon, there must exist a delta for which whatever, right? And again, delta has to exist, but we have control over delta. This doesn't have to work for any delta given that it works for any epsilon. We could rearrange the definition and say for any delta, but then we would have to do their existent epsilon, right? And we could then examine the inverse function, for example. So one of them has to be for any, and the other has to be there exists. And in this case, this is delta. So it's not predetermined. We can actually choose delta conveniently, and we'll see why this will be important later. Our freedom to choose this conveniently, and this is done as the last step usually. So this is kind of the crux of the proof, right? We let x minus a, absolute value of that, be between 0 and delta, strictly between. And then we must show that this statement, that this statement right here, implies that value of f of x minus L is between 0 and epsilon. And so basically we want to rearrange x minus a into f of x minus L. We express f of x minus L in terms of delta, and then we use this expression to see what value of delta in terms of epsilon will be convenient so that this, in terms of this, which is less than delta, will be less than epsilon. And so then we see what's convenient, we just write that, and we plug it back in. So I'm going to demonstrate how this works on a couple examples, if that sounds a bit unfamiliar. So problem 1. And I'm going to start with a really basic example here. Literally can be done by direct substitution, but that's not formal, right? We need to do epsilon delta. So limit as x approaches 0 of x squared is equal to 0. We need to show that. So for any epsilon greater than 0, we there has to exist delta equal to blank. We don't know yet. We will express this in terms of epsilon when the time comes. So let 0 less than x minus 0 less than delta x minus 0 luckily simplifies to just x. This will almost never be the case unless the value at which we are taking the limit is actually 0. So now we have to do f of x minus L, and we have to convert it into this somehow to express it in terms of delta, which we can express in terms of epsilon using the expression we got here. So x squared minus 0 is just absolute value of x squared, right? Pretty easy simplification. But then notice that absolute value of x is less than delta. And so absolute value of x squared will be less than delta squared. But now we must show that this is less than epsilon. We already have less than sign. So as long as we have delta squared equals epsilon, we're good, right? We have f of x minus L, absolute value of that is less than epsilon. And to make delta squared equal to epsilon, we will have delta equals root epsilon, right? This is the last step I was talking about. We have to determine what this is going to be equal to make this conveniently simplify. We then plug this into this expression to complete the derivation that the limit as x approaches 0 of x squared is equal to 0. So let's do another example. So problem 2. Show that the limit as x approaches 1 of the square root of x plus 3 is equal to 2. So the first step is for all epsilon bigger than 0, there exists a delta equal to whatever. All right. So we let x minus 1 absolute value that less than delta. Again, so I am dropping the zeros, this part like bigger than 0 in a lot of these cases, just because it takes up space, and typically this step showing that it is less than epsilon is much more important than showing that it is bigger than 0. So that is definitely a step, but I'm going to omit it for now just to speed things up. So absolute value of square root of x plus 3 minus 2 is equal to, so here to simplify square roots, we typically multiply by conjugates. And although we typically do this to get a square root out of a denominator, now we're doing it to get it out of the numerator. So I will show why this makes sense later. And so after completing this numerator using difference of squares, we get absolute value of x minus 1. So this is immediately a good sign because we recognize x minus 1. This is less than delta. But how do we express this in terms of x minus 1? Well, let's go to our little bubble right here. We can notice that absolute value of x square root of x plus 3 plus 2 is always greater than or equal to 2, right? This isn't a strict inequality because x could be negative 3. And so this implies that 1 over absolute value of root x plus 3 plus 2, which is exactly what we have here, is less than or equal to a half, which is perfect because we can plug that back in. So we have that this is less than x or equal to x minus 1 over 2. So f of x minus L is less than this. But then we plug this back in, and we have that this is less than delta over 2. So actually, this blue bubble turned out to be really convenient because had this been a greater than sign, we would have had a greater sign here and a less than sign here. We wouldn't have achieved any results. But we have something is less than or equal to something, which is less than something, so this less than still applies. And now we have that f of x minus L absolute value of that is less than delta over 2. As long as delta equals to epsilon, this will always be true, and so that is why limit as x approaches 1 of root x plus 3 is equal to 2, because this definition holds. Okay, so hopefully that gave some practice with epsilon delta. There's one more thing I want to cover in this video. I won't go into as much detail about this special case, but what if a is plus or minus infinity? That is, what if there is a finite limit at infinity? So an example of this would be 1 over x that has a finite limit of 0 at both infinities. So what happens in that case? Because we can't really write x minus a is less than delta in this case anymore, right? So let's draw this graph, and suppose we have this function. This function we'll call f, and we also have this limit, which we'll call L. So it approaches this red line, this red asymptote. And so we again have our range, L plus epsilon, L minus epsilon. In this case, L minus epsilon is below the x-axis, but that doesn't really matter. And instead of defining a delta, we will define this value n. So this will be our analogy of a delta, right, in this case. So basically, this definition says that for any epsilon, there must exist an n for which x is bigger than n will imply that f of x minus L is less than epsilon. And if this is negative infinity, then it's x less than n. So what is this definition saying? Well, we can decrease or increase epsilon, and we can increase and decrease the size of this range. There must still exist an n for which, for all values of x that are bigger than n, we will have that f is in this range right here. And n in this case turns out to work. This n, for example, right? No matter what, as we go forward, this f will be smaller in magnitude than L plus epsilon. So now let's see why this breaks down. Again, in this case, it is also still helpful. Why does it fail when it fails? So for example, f of x equals sine of x. This does not have a limit at x equals infinity or x equals negative infinity, but it oscillates. But this now gives us the tools to show why. Because for arbitrarily small epsilon, right? Because again, epsilon could be as small as we are given, right? The oscillations will prevent us from choosing this n. So with this, we will wrap up epsilon delta. I will leave one challenge problem. So the challenge problem is prove that c times the limit as x approaches a of f of x is equal to the limit as x approaches a of c times f of x. And this is a basic limit property, but we want to use epsilon delta to prove this. Okay, that's it for today. Hope you enjoyed this video. Leave any comments in the comments, and I will post some of the sources that I used to make this video. And thanks for watching.